We're cooking.
Hello, I'm Professor Rios. I'm the Professor of Electrical and Biomedical Engineering at the Bryan University for ECT 220. And I'll be explaining how you can calculate the voltage collector emitter from this circuit. The first thing we need to do is to find the voltage equivalent Thevenin and the resistance equivalent Thevenin for the base. Okay. In order to do that, the first thing we need to do is to short out the power supply. Therefore, these two resistors will be in parallel. That's how we calculate the R Thevenin, as is described in this formula. R Thevenin is R1 and R2, which is the resistance from the power supply to the emitter to the base, and from the base to the emitter. These two resistors are in parallel. The end result is 3.55 ohms. Now the voltage Thevenin, you use the voltage divider rule, which in this case we multiply VCC times R2 divided by R1 plus R2. Please note that R2 is the resistance at the base emitter connection. Okay. Now we substitute the values and we get 2 volts. That's our R Thevenin. Now, in order, once we have the R Thevenin, which is described in this circuit here. Okay, this is our transistor. That's R Thevenin. That's voltage Thevenin. This is our RE. Okay, the current in this loop is what we would call IB. Okay, actually current at the base. IB. Current is voltage over resistance, right? Now, this resistance is going to be whatever voltages we have in this loop divided over the total resistance in this loop. It's a very important point that we're going to reach out. Now, current at the base is going to be voltage, Thevenin voltage, minus the 0.7 volts, which is the base emitter forward biased voltage of the transistor, okay, divided by the total resistance. What is the total resistance in that circuit? It's going to be R Thevenin, which is our value of 3.55K, plus the resistance in the circuit, in the emitter. But now, something very interesting happens in this situation. The value of this resistance, since it passes through the transistor, the value of the resistance is reflected back at the base circuit by a factor of beta plus 1. Okay? And if you look at the resistor from the emitter point of view, it's just the resistance of the emitter. But the resistance of the emitter is reflected back in the circuit of the base by a factor of RE multiplied by beta plus R1. This is of key importance to calculate IB. Again, the current at the base is equal to the total voltage in this circuit divided by the total resistance of the circuit. Now the total voltage of this circuit is going to be voltage Thevenin minus the 0.7 volts of the junction base emitter divided by the total resistance. The total resistance is R Thevenin plus the resistance that reflects back to this circuit from the meter. And that is the resistance at the meter multiplied by beta plus 1. And this is something that you just take it like that. Okay? Once we find this, we substitute the values and we calculated that IB is equal to 8.38 microamps. Now, after we have IB, we know that IC is going to be beta times IB. Therefore, our IC is going to be 0.84 milliamps. Okay? Since we're trying to calculate the voltage base emitter, the voltage collector emitter is going to be the voltage of the power supply minus the voltage drop in this resistor minus the voltage drop in the resistor is going to be the voltage collector emitter. And that's what we have here. Voltage collector emitter is equal to VCC minus the current of the collector multiplied by the value of those two resistors. Okay? Why can we do it like this? Because the current of the meter is very similar to the current of the collector. Okay? There is very little difference between the current of the collector and the current of the meter. That's why we take it as a valid value. And that's how we calculate the voltage collector emitter, which ends up to be 9.6 volts. Okay? Thank you.